Okay, I've already uploaded yesterday's lecture material into the e-learning. I've also uploaded the instructions for test 1 tonight. Yeah. So this is the instruction. Oh, let me first share you my computer screen. Okay, tonight we're going to have test 1. So integrity form. Yeah, I've also the integrity form in the e-learning. I also given it to you also through WhatsApp. So please submit this integrity form. Yeah, this form here. Yeah, before test 1. Yeah, before test 1. I noticed that some of you have already submitted in the e-learning. Yeah. And then, okay, where's the timeline again? Okay, here. Right. So please scan your QR code for attendance starting 8:30 p.m. You need to go to WebEx and then to see the QR code. And then 5 minutes before 9, I will release the test 1 through questions through WhatsApp and also in e-learning. Then you start answering here at 9 p.m. The duration is 75 minutes, yeah, for test 1. And 10:15, everybody should stop writing. And then you're given 10 minutes, yeah, to compile, scan, and submit. You please submit in a single PDF file. We'll create a portal in the e-learning for test 1 submissions. Yeah. So please do this within 10 minutes. Otherwise, you'll be penalized for late submissions. Yeah. Any question regarding test 1? And yeah, please also use this front page, okay, when submitting your solutions. Yeah, I've also given this through WhatsApp a few minutes ago, so you can fill this out earlier. Yeah, then use this as a front page of your submissions.
Doctor, can the
Yeah,
submission time maybe add on a 5 minute because we need to compile again with this first page?
compile again what? No, 10 minutes. Only 10 minutes is given.
Okay.
Okay, only 10 minutes is given. Yeah. So please do this quite quickly. Mm. Yeah, this is the practice, okay, for other tests also. Yeah. Any more question? Any other question regarding test 1?
Doctor, the front page we
Mhm.
can get from where?
I've already sent it through the WhatsApp group. I've already given it to you through the WhatsApp group for this course, for this class. Can you
Oh,
please check
okay.
your WhatsApp
Thank you,
now?
doctor. Mhm.
Can you please check your WhatsApp now? Do you see it?
Okay. I see it. I
Okay,
just see it
okay.
just now.
All right. Any other question? A question regarding test one. I'll continue with my lecture.
Doctor, can I
Yeah.
ask if
Mhm.
suddenly Wi-Fi lag, can have other option to submit the PDF file others than e-learning?
In case e-learning fails, then you can submit it directly to me through WhatsApp. Yeah.
Okay, thank you,
Okay.
doctor.
Yeah. But try using e-learning first. Yeah. If e-learning fails, can submit directly to me through WhatsApp. Yeah. So if e-learning fails, submit to me through WhatsApp. Huh? Oops, what happened? Through WhatsApp. Okay. Not through the WhatsApp group. To me. Okay. Just to me only. Yeah. Don't submit it through the WhatsApp group. Yeah. Anything else? Okay then. Let's continue with our lecture. I have discussed double integrals. Um, let- I've discussed this area problems related to double integrals. Let's see one example of volume problems using double integrals here. After that, I will uh, discuss double integrals in polar coordinates. So here define the volume, say under the plane z equal to 1 plus x plus y over the region bounded by the curves this question I've already written yesterday, but you don't have time to solve it, so I'm writing these questions again. Okay, this is the volume problem. Finding the volume under the plane z equal to 1 plus x plus y over the region bounded by the curves. So it is a good practice, to sketch the region first. Whenever you get this kind of problem, it is a good practice to sketch, to make a sketch of the region first. So we have the two curves here, y equal to x squared and y equal to 2x squared. So both are parabolic curve. So this is one of them. And 2x squared is higher, right? It's higher than x squared. So this is y equal to 2x squared. And this one is y equal to x squared. And then the region is bounded by x equal to 1/2. Because this is 1. This is half and 1/2. The line x equal to the vertical lines x equal to 1/2 and x equal to half. So the region is this green shaded region here. We denote the region as R. So this is the region bounded by the 4 curves there. Okay. So we want to find the volume under the surface over this region R. So notice that Z here is positive, right? Observe that Z equal to 1 plus X plus Y is positive over the region R. For the volume problem, we want the surface to be above the XY plane. Okay, must be positive. In that case, must be positive. Then only it can be treated as a volume problem. So recall that volume is equal to the double integral over the region R f xy dA. Okay, dA. This is the, and in this case fxy is z. This is this is this is our fxy here. So as you can see here, R is bounded by R consists of all points x, y. X is bounded between numbers. X is between half and 1. Is this? X is bounded between a half and 1, while Y is bounded between x squared and 2x squared. So what is the order of integration that I should use here? Is it dx dy or dy dx?
dy
Yes?
dx.
Dy dx, right? Because y is bounded by curves. So we should use this order, dy dx, because y is bounded by functions of x. The lower limit is x squared, the upper limit is 2x squared, while x is bounded by numbers. So this is the setup, okay, of the double integrals for calculating the volume. So first we uh, evaluate the inner integral with respect to y. What is it? What is the integral of 1
Y plus
x
xy.
plus y
Y plus xy
with
plus y
respect to
squared over
y?
2.
Okay, 1 plus x is a constant, so we can write it as the integral as 1 plus xy or y plus xy. Okay, and then 1/2 y squared. This to be evaluated between y equal to x squared and 2x squared. Okay, so first we substitute y equal to 2x squared with 2x squared. Okay, and then substitute y equal to x squared. Let's put a bigger bracket around there. So now it reduces to a single integral with respect to x. It's a matter of simplifying all this first before before integrating. So we have 2x squared plus 2x cubed, 2x squared is 4x to the power of 4 is 2x to the power of 4. Okay. The minus, we have x squared plus x cubed plus 1/2 x to the power of 4. Okay. Let me simplify here. Uh, 2x squared minus x squared is x squared. 2x cubed minus x cubed is x cubed. 2x to the power of 4 minus 1/2 x to the power of 4 is 3 over 2 x to the power of 4. Okay. So this is a simple integral. I'm sure everyone is able to solve it. So let me just show you. The answer is 49 over 60. Because this we are dealing with volume, so we use unit cube. Okay. So I leave it to you to evaluate this single integral. Should be no problem. Should be okay. You have learned how to evaluate the single integral. Any question for this example? So making a sketch is important, you know. This helps you to determine the appropriate limits for x and y. And diagrams also carry marks, you know, for tests and finals. Diagrams also carry some marks. Yeah. Even I need to draw diagrams in order to solve this question. Yeah. Otherwise, how would you know, be able to come up with the limits, correct limits or double integrals? Any question?
So far, so good, Doctor.
Okay. Okay. Thank you. All right. Now let's discuss this topic. You know, double integrals in polar coordinates. Yeah? Double integrals in polar coordinates. Mm, application of double integral, area, volume. We have discussed some of this also. Area problems and volume problems related to double integrals. Okay, now let's discuss this topic, double integrals in polar coordinates. Okay, you have studied polar coordinates before, right? In mathematical methods 1. Okay, let's consider this problem. It's evaluating of a double integral fxy, where the region is over the region, the circular disc D here. Okay. So the domain D can be described by this set here, set xy, where x squared plus y squared less than or equal to r squared. Yeah, it's a
Doctor,
disk of
sorry.
yeah.
You are not showing the what yeah. Wait.
I'm not showing. Can you see it now?
Yeah, I can see now.
Uh,
Thank you, Doctor.
maybe sometimes internet a little bit slow, right? uh,
Yeah, got lagging at
mm,
my side maybe.
mm-hmm. Yeah. Where are you from? Where are you staying? Where are you staying?
I'm staying at Cheras, but don't know
Oh,
why. It got my
okay, okay.
Cheras Selangor.
All right. Okay. Consider this the evaluating of double integral over a circular region D here. So, uh, so obviously, y if it the equation of the circle is x squared plus y squared equal to r squared. So the upper curve, if we solve for y, then we get y equal to plus or minus, right? If we solve for y, then we get y equal to plus or minus the square root of r squared minus x squared. The plus sign refers to the uh, top part of the curve, while the minus sign refers to the lower part of the circle here. Okay, so you can think of the region D being bounded by the upper semicircle and bounded below by this lower semicircle here. So this is the setup for the evaluation of the double integrals using Cartesian coordinates xy. So it looks complicated, right? It's complicated. If the region is circular, then the double integrals in terms of x and y has this form here. So another choice, sometimes it's more convenience for circular regions. It is actually more convenience, to use the polar coordinates here. Okay, you have studied polar coordinates, right? We have this relationship between x and y. We have x equal to r cos theta, y equal to r sine theta. Yeah. So if I have a suppose this is the point r theta here. Oops, not visible. Let me use in black then. Oops, where has it gone? Where has it gone? Where has it gone? Oh, yeah. So suppose they have a point there, and in terms of polar coordinate, r measures the distance, right? R measures the distance of the point r theta from the origin O, and theta measures the angle from the positive x-axis. Yeah. So, in terms of polar coordinates, the region D, the circular region D, consists of all points r theta such that r is between 0 up to the radius of the circle, and this is a complete disk, so theta varies from 0 up to 2 pi. So you see, we have a simple representation of the domain D in terms of polar coordinates compared to Cartesian coordinates. Yeah. Yeah. So So we use this relationship between Cartesian and polar coordinate to write fxy in terms of, we replace x here by r cos theta, and we replace y here by r sine theta. And the limits 0 to r, 0 up to 2 pi. Now, what is the area element? Is for Cartesian coordinate, the area element is dx dy. What is the area element for polar coordinate? Is it dr d theta? Or is it d theta dr? The answer is no. Surprisingly, the answer is no. In fact, the area element should be r dr d theta. Okay, why is that? Why? So let's see, can understand that. Suppose this is a region bounded by the blue curves here as shown here, right? Now, if I use, if this is in terms of rectangular coordinates, then we partition this blue region here in terms of rectangles, okay? In terms of rectangles, yeah, as shown here. If we use rectangular grids, if I partition this blue region using rectangular grids, then we have sums of rectangles, right? We have some sum of rectangles. We have sub-rectangles in this blue region here. And that's what we call dx dy for each rectangle or the area element here. Now, if we consider polar coordinate, if I use polar grids, okay, then each sub partition here is no longer in the form of a rectangle. Okay, if we partition the blue region here using polar grids, then the partitions, okay, they are no longer in the form of rectangles. We have something like this here. The area element has bounded by straight lines and two circular curves here. Yeah? If we use polar grids. So if the think of dA, yeah, think of dA as d. Okay, we have r here, right? From this point, from these points to these points. Okay, from this point to these points. Consider a small increment. You can think of dA as being a small increment from r to r plus dr. Think of dr here as a small quantity here. Then dA has sides dr, right? Has this radial sides dr. Because r plus dr minus r is dr. Okay, what about the circular part here? It is an increment from theta up to theta plus d theta. Okay, look at the radial lines here. The lower radial line has angle theta. The upper radial line has theta plus d theta. Again, think of d theta here as small. So the angle between the two radial lines here is d theta. Okay, d theta. What is the length of this circular arc here? So using circular measure, okay, using this circular measure here, if the length of this curve S here is r theta, right? the formula is r theta. So using that formula, the length of this circular arc here is r times d theta, because the angle subtended between these two radial lines here is d theta. So dA, okay, for very small dr, dA is approximately r d theta times dr. Okay, yeah, even though it is not a rectangle, but it is approximately equal to r dr d theta. Yeah, it is approximately equal to, and the approximation gets better and better as r dr gets smaller and d theta goes to 0. Okay, so here we have this so the double integral fxy with area element dA, okay, can be in terms of polar coordinates. We replace x by r cos theta, y equal to r sine theta, and dA becomes r dr d theta. Okay, in this setup, we have the region R such that the radius is bounded by two polar curves, r greater than h1 theta, less than or equal to h2 theta. Okay, and the theta is between alpha and beta. So this is the setup, or this is the conversion of the double integral from polar coordinate to from rectangular coordinate to polar coordinate. All right. Okay, let's see an example of evaluation double integrals in polar coordinate. For an example, suppose D is a region as shown below. Evaluate. Okay, this is the region. It is bounded by two circular arcs here. Right. So this is x and y. So this is the region D here. Okay. So we want to evaluate this double integral. 3x plus 8y squared dA. So notice the region D, there are it's a circular region, right? Bounded by the lower semicircle with the upper semicircle. So it is preferable to evaluate this double integral using polar coordinates. So think of this region D consisting of all points r theta. So what are the bounds for r and theta here? What are the bounds for r and theta? R is between
2 and 1.
R is between greater than 1, right? Greater than 1, smaller than 2. Okay, what about theta?
180.
Between 0 until um, we use radian, huh? Not degrees. We must use radian
Pi.
mode.
To pi.
Pi, yeah? Pi. Okay. So you see how simple the region D is when written in terms of polar coordinates. Yeah. If you try to use Cartesian coordinates, it involves square roots. Yeah. In fact, you have to split this domain into two. Yeah, if you want to work this to evaluate this using Cartesian coordinates, so it is much easier. Yeah. It's more, I mean, more convenience to evaluate this integral using polar coordinates. Because the bounds here for r and theta are numbers. So therefore, the double integral, okay, we replace x by r cos theta and replace a y in the integrand by r sine theta. And dA becomes r dr d theta, right? R dr d theta, yeah, according to our previous discussion. So here I have written the double integral in polar coordinates with the order dr d theta. So that means the inner integral is with respect to r, and r has limits 1 and 2. The outer integral is with respect to theta, and theta has limits 0 up to pi. Okay. So let's simplify the integrand. First, we have 3r cos theta plus 8r squared sine squared theta. Oh, we have r outside. So we have 3r squared here actually, plus 8r cubed. Yeah? So dr d theta. So integrate, evaluate the inner integral first. What is the result? Integrate with respect to r first. What is it?
6r cos theta.
R
6r cos
cube
theta.
cos theta, isn't it?
R cube, yes, R cube.
Oh, sorry,
What
doctor.
else? What about the second term?
4R, 2R cube
Two
sine.
R, no, two R, not cube, but to the
Cosine
power of
squared. Yes, yes.
4. Yeah, yeah. So R is between 1 and 2. So first we substitute R equal to 2, so we get 8 cos theta plus 8 cos theta. 16 times 2 is 32. 32 sine squared theta. And then we substitute r equal to 1. We get cos theta plus 2 sine squared theta. Alright, so now we have reduces to a single integral with respect to theta. Let us first simplify the integrand. 8 cos theta minus cos theta is 7 cos theta. 32 minus 2 is 30. Right? So that's the integral, single integral with respect to theta only. So can I leave it to you to evaluate this single integral? Show that the value is equal to 15 pi. Okay, I leave it to you because I'm sure you have done this many times before. Evaluating integrals using cosine and sine squared. The integral of cosine is sine, right? The integral of cosine is sine. What about sine squared theta? We need to use some identity. We have the identity cosine 2 theta is 1 minus 2 sine squared theta. Therefore, sine squared theta is 1 minus cosine 2 theta over 2. Okay, so the suggestion here is to replace sine squared theta by 1 minus cosine 2 theta over 2, and then you perform the integration. Okay, I leave it to you to do the calculations and show that the answer is equal to 15 pi. Any question for this example? This is a sample test 2 question, Sample test 2 question. See, the first question is about evaluating double integral in rectangular coordinates by first changing the order of integration. Okay, I've done one example for such question. The second question, compute this double integral here in polar coordinates by first changing it to polar coordinates. Yeah. Let's try this for our next example. This is a sample test 2 question here. Okay, it is suggested that to change this, to evaluate this integral by changing it to polar coordinates. Of course, the reason is to make life easier. Okay, look at the given limits here. What is the region R for this double integral? Okay, it is clear, isn't it? From the limits of the double integral, that the region D consists of all points x, y, such that x is y. You see, the inner limit is y. The inner, the order is dy dx. So the outer limits are for, the limits of the outer integral is for x. So x is between numbers 1 and 2. While the inner integral is with respect to y. And according to the given limits, y is greater than minus square root 3x and y greater than less than 0. Okay, so this is the domain for the double integral. So from the limits given, we can deduce what is the domain here. Okay, let's make a sketch of this domain. We have x between 1 and 2. Okay, we have y equal to 0 is the x-axis, is the y-axis. Okay, let's look at the one of the curve is y equal to square root 3x, right? One of the curve is y minus square root 3x. It is a line, isn't it? It is linear. It is a line. Y equal to minus square root 3x is a line that passes through the origin. That passes through the origin. It's negative. Negative. So suppose this is the line. Doesn't have to be really accurate. Yeah. So suppose that is the line y equal to minus square root 3x. And x is between two lines, x equal to 1 and x equal to 2. So must be this region, isn't it? Must be this region. See? So y is bounded below by the line y equal to minus square root 3x. This is y equal to minus square root 3x. The x-axis is the line y equal to 0. And here is the point 1 and 2. X between 1 and 2. Okay. So, okay, how to change this to polar coordinates? By first changing it to polar coordinates. R d theta. What about R here? What about R? So we have a point R here. Okay? R there. Is the angle theta. So what are the limits for R? So R is between x equal to 2 means what? We have to convert x equal to 1 into a polar coordinate. R cos theta equal to 1 and x equal to 2 means R cos theta equal to 2. So therefore R is 1 over cos theta. For the second line x equal to 2, R is 2 over cos theta. So you can see here R is between 1 over cos theta and 2 over cos theta. Okay, what about the angle? The angle is from the positive x-axis to the line, to that line y equal to minus 3x in the negative direction. Okay, so theta is between what? What is this angle here? So the slope, what is the slope here? What is this angle here? This line here makes what angle with respect to the x-axis? we have tangent theta equal to minus square root 3. So theta is minus what? Pi over 6, pi over 3, right? Because tangent 60 degrees is square root 3. Yeah, so the angle there is minus pi over 3. So we can say that the angle theta runs from minus pi over 3 up to 0. So that is the region D in terms of polar coordinates. And okay, so now we go back to the given double integral. So we have the double integral 1 up to 2 minus square root 3x0 1 over x squared plus y squared to the power of 3 over 2 dy dx. Okay, so what is the setup for this double integral in terms of polar coordinates? First, notice that x squared plus y squared is equal to what? X is r squared cosine squared theta plus y squared is r squared sine squared theta is equal to r squared, right? R squared. Yeah. So downstairs we have r squared to the power of 3 over 2. And the element is what? R dr d theta, isn't it? R dr d theta. Yeah. The area element in polar coordinates is r dr d theta. So r is bounded below by 1 over cos theta and bounded, what happened here? Bounded above by 2 over cosine theta, and r theta is between minus pi over 3 up to 0. Okay, so what is it? We integrate first with respect to r. Hmm. First we simplify, we have r over r cube, isn't it? We have r over r cube, which is 1 over r squared. 1 over r squared is the same as r to the power of minus 2. So we integrate first with respect to r. So the integral is minus r minus 2 minus 1 over r, isn't it? Minus 1 over r. Yeah. Okay. So let's pull out
Sorry,
the
doctor.
minus sign.
Can I
Yeah.
can I ask a question?
Uh-huh.
The r squared times r squared to the power of 3 over 2. It should
Uh-huh.
is it should be become r to the power of cube. R to the power of 3. We
Yeah.
can cancel out the 2, right?
Yes.
Then you write it
Yeah.
as
This is r
r.
cube, right?
Yeah.
So we have
Got
r
r here.
upstairs. We have r
Okay.
upstairs. So it is 1 over r squared,
Sorry, doctor.
which I have written as r to the power of minus 2. Yeah.
Oh, thank you, doctor.
Okay. So let's pull out the minus sign. Okay. What is when r is 2 over cosine theta, the reciprocal is cosine theta over 2. when r is 1 over cosine theta, the reciprocal is cosine theta. Okay. Yeah. So and then so cosine theta over 2 minus cosine theta over 2 is minus cosine theta over 2. Minus and minus give us, make it plus. 1/2, right? 1/2, yeah. Okay, so I'm sure everybody can solve this double integral, a single integral with respect to cosine. All right, so I leave it to you to complete, the calculation, right? Any question? It is not easy, isn't it? If you look at the original integral in the polar in rectangular coordinate, it's not easy to integrate with respect to y first, isn't it? I don't have any idea at the moment how to integrate this with respect to y first. Mm. Maybe it's possible, but it's not easy. Yeah, more. So it is easier to work with the polar coordinate here. Let's not have a 10 minutes break. Uh, let's just continue, okay? Is it all right with everybody?
Okay, sir.
Okay, then we can finish around earlier, around 12:40. Yeah. Uh, I need to plug in the power cable. Okay, let's look at another example related to volume problem. Determine, this is also a sample test final final exam, sample final exam. Determine the volume of a solid bounded by the paraboloid z equal to x squared plus y squared, and the plane z equal to 4 using double integral in polar coordinates. Yeah, this is a sample final exam question related to double integral, polar coordinates, and volume. It is good, to make a sketch also for this problem here. All right, so here we have a three-dimensional axis, x, y, z, paraboloid. So this is a common surface, yeah. So everybody, should know what it looks like. This is a paraboloid. Yeah. And then we have a plane. So this paraboloid, we cut it with a plane. Cut it with a plane. So this is the plane that passes through. This is z equal to 4. And this is the paraboloid z equal to x squared plus y squared. Now it will the plane will cut the paraboloid, yeah, will cut the paraboloid. So how to find the volume between the paraboloid and the plane z equal to 4? So we know here that z is between, we know here z is between x squared plus y squared and less than 4. Okay, yeah, we know the region is shown here. What about xy? What about xy? Uh, so if what are the regions? What about the domain for xy? So if I make a projection, then this is the domain for xy. Okay. Yeah. Or in other words, if you uh, put a torchlight, from above, and it will cast a shadow, right? If you put a torchlight from above, then the object will cast a shadow. Right? This three-dimensional object, solid object, will cast a shadow on the xy plane. If you were to shine this tree from above, okay, then it will cast a shadow, this green shaded region here. So this green shaded region is the domain D, okay, for the object under consideration here. So this is circular. This is a circular region on the xy plane. This is a circular region on the xy plane. What is the radius? What is the radius?
2. The radius
How
2.
do you know it's 2?
Because square root of 4 is 2.
Uh-huh.
So that the
We
radius
have
is 2. Yeah, from the
the
equation
yeah,
x2 plus x squared plus y squared equals to z r squared.
yeah.
So radius
We
is
have these
2.
two equation, right? We have these two equation. So z equal to 4, right? the horizontal plane cuts the paraboloid at z equal to 4, right? So therefore we have x squared plus y squared equal to 4. This circle here, okay, is x squared plus y squared equal to 4. Yeah. So it is a circle of radius 2. Yeah, radius 2. So the domain D, in terms of polar coordinate, is r between 0 and 2, and theta, it is a complete disk. So theta is between 0 up to 2 pi. All right. So what is the volume? It's a double integral. Let's first write it in terms of x and y. The volume is the surface bounded by, the upper surface is 4, and the lower surface is z equal to x squared plus y squared. This is the setup of calculating the volume bounded by two surfaces. The upper surface is 4, the lower surface is z equal to x squared plus y squared. And this is in terms of polar in rectangular coordinate. Okay, so now we convert this into polar coordinates. So we replace x by r cosine theta and y by r sine theta. That is equal to r squared, isn't it? R squared. And then dA is r dr d theta. Okay. And the inner integral with respect to r is between 0 up to 2, and the outer integral with respect to theta, so theta is 0 up to 2 pi. So we have this integral. So this is the same as 4r minus r cubed. If I multiply r into the bracket, it is 4r minus r cubed. So actually I can write this as a product of two single integrals, because the function rt, the integrand here is is a product of two functions, one with respect to r alone, and the other is just a constant. Okay, it's just a constant. So the integral with respect to theta is just 2 pi. What about the first integral? It is 2r squared minus 1 over 4 r to the power 4. R is between 0 up to 2. Okay. So first we substitute r equal to 2. Okay. 8 minus what? 8 minus 16 over 4. That is 4. So it is equal to 8 pi unit cube. Okay. Yeah, that's the way. Any question for this example? Let's consider another example. Evaluate this double integral xy dx dy where the domain D, where the domain D is bounded by r equal to sine 2 theta, and theta is between 0 up to pi over 2. Okay. So the double integral is in terms of rectangular coordinates. However, the domain D is in terms of polar coordinates. So that means you must use polar coordinates to evaluate this double integral. Yeah? Even though it doesn't say that you need to change it to polar coordinate, but it is understood here, right, that you need to evaluate this double integral using polar coordinates. Yeah. So it's a good idea to sketch the region also. In mathematical methods 1, you have seen engineering mathematics 1, you have seen some polar coordinate, polar curves. Yeah. So it is actually a petal in the first quadrant here. See, when theta is 0, r is 0. When theta equal to pi over 4, when theta equal to pi over 4, it is sine pi over 2. So it is the length here. The length here. The tip here is equal to 1. And then when theta equal to pi over 2, we have r equal to sine pi, so it goes back to 0. So this is the region D for this problem here. So what is this double integral in terms of polar coordinate? We know that we need to replace x by r cos theta and y by r sine theta, and x dx dy become r dr d theta. So clearly from the description of the domain D, the r is bounded between 0 up to sine 2 theta, while theta is between 0 up to pi over 2. So this is the double integral here. Totally in terms of polar coordinates. Yeah. So let's simplify the integrand first. Sine 2 theta. We have r cubed, right? We have r cubed. So I can also write this r cubed outside the integral with respect to theta. And inside we have cos theta sine theta. Okay. So here we have r cubed sine theta cos theta. And sine theta cos theta is using identity is the same as sine 2 theta over 2. Okay. Yeah. It's easier to work with this by first expressing sine theta cosine theta, because why? Because recall that sine 2 theta is 2 sine theta cos theta. Sometimes you need to recall, some of these trigonometric identities when evaluating double integrals in terms of polar coordinates. Yeah. No, I'm sorry, I cannot pull out R. R has to be still inside. R has to be still inside because we are integrating with respect to R. So we must have R cube inside here. Okay, so what is the integral of R there? Let me pull out 1/2. What is the integral of R cube? It's, yeah. Anybody?
R
R
over
to the power of 4 over
8.
4, isn't it? I pull out 1/2. Can you see it? I pull out 1/2 already. So the integral of R cube is R to the power of 4 over 4. Yeah, and R is between 0 up to sine 2 theta. So 1/2 times 1/4 is 1/8. So first we substitute sine 2 theta. So we get sine 2 theta to the power of 4, which is 1 over 8 times the integral 0 over pi over 2. We have what? Sine to the power of 5 of 2 theta d theta. Any idea how to evaluate this? Okay, one way is to first let's make the substitution u equal to 2 theta. Therefore, d is equal to 2 d theta. Right? So 1 over 8. Then theta is pi over 2. U is equal to pi. So now we have 1 over 6. Okay. Yeah, it is some thinking in life as sine
Doctor, we can hear you.
u to the power of sine squared u to square time sine u du. You cannot hear me. I'm still.
You are lagging, sir.
Can you hear me now? Can you hear now?
Sudden can.
Maybe internet problem. Because it's maybe it's internet problem. What about others? Can you hear me clearly?
No, also, doctor.
I don't know. Maybe it little. Hmm. Can you hear me?
Suddenly
Is it
can.
okay
Suddenly
now?
can.
No, doctor.
Can you see the computer? Can
No.
you see the computer
No, I
screen?
cannot see. I cannot see the computer screen. Yeah, it's blacked out.
I think because of the Wi-Fi of doctor is not stable now.
Oh, do you think the problem is over here at UTM? Uh, but I seem to have a good connection here. But okay. Um, and so okay, since you can see my computer screen, I can finish off this problem. Okay, now we express one sine squared as 1 minus cosine squared. Okay, the trick is to rewrite sine squared as 1 minus cosine squared. And then we make the substitution. Let's make the substitution W equal to cosine U. Then we have dw minus sine U U. Right? Yeah. So then the integrand can be written as 1 minus W squared squared. And so du is minus dw. Okay, minus dw. What about the upper and lower limit? Yeah. Hello?
Doctor, I can see the screen.
Yeah, me too.
Cannot see the screen. But I'm still sharing the screen.
The screen just say that doctor is starting to share content, but it's nothing.
Is it just is this happening to just
Hello?
Hello?
Is it okay now?
Yes,
No,
Uh,
doctor.
no,
We can
no,
hear you,
can
but
hear,
we can't see
but
the screen.
no, the content.
Hello? Is it okay now?
No, we can't hear you, doctor, and we can't see the screen.
we cannot see the screen. Doctor.
Yeah, even you're seeing the screen yet. Can you see it now?
I still cannot see it.
I don't know. Uh, I have internet connection here. No problem with the internet connection. Probably it's on your part. Who can see this computer screen? Can somebody respond?
I can see. I can see it now. I can see it
Now
now.
we can see it, doctor.
Nobody can see it. All right. So let me continue with the calculation. So we make this substitution, okay, to rewrite this integral in terms of w. So we have a minus 1 over 16, the integral 1 up to minus 1, 1 minus w squared squared. 1 minus w squared is the same as 1 minus 2w squared. 1 minus 2w squared plus w to the power of 4. Now, since we have a minus sign in front of the integral, that means we can interchange the upper and the lower limits. All right. So I'm going to leave it to you to evaluate this integral and show that the value is equal to 1 over 15. 1 over 15. Okay. So sometimes, so in this example, sometimes you need to recall some of the techniques of integrations that you have studied before. Any question? Any question?
No, doctor.
Hmm. Let me put this headphone back on so that we. Okay. All right. So I've shown you several examples of double integrals in polar coordinates. What next? Applications. Yeah, let's look at applications of double integral. I have mentioned some examples related to area, volume. Okay, let's take a quick look about mass, application of double integrals in calculating mass. Okay, let's take a quick look about this application of double integral for calculating mass. Let me show you how the double integrals looks like. And I think after that, discuss examples in our next lecture. So what is a lamina? Lamina is a thin sheet of material. And think of like a thin metal plate. Okay, very thin. Yeah. So like it's like a two-dimensional object. Yeah. Suppose we have a lamina. Okay. Uh, okay, we have this relationship between density, mass, and area, right? The density is equal to mass over area. So mass is usually it has unit in terms of kilogram. Area is in unit squared. So density is a kilogram per area. Yeah. So density is usually denoted by the Greek symbol rho. Yeah, rho. Yeah. And mass is usually denoted by a letter small m, while area is denoted by capital A. So this relation can be written as rho equal to m over A. So therefore, mass is equal to rho times A. Now, this is easy if everything is constant. Area is known, mass density is known. So then mass is just density times A. Now, what if we have a variable density? Okay, suppose we have a lamina here as shown, and suppose the density of the lamina varies from point to point. So we can think of the density as a function of x and y. Yeah, as a function of two variables x and y. That means the density may varies from point to point on the lamina. So the question is, what is the mass of the lamina? Yeah. So we use an approximation approach first. Yeah. So first we partition the lamina into small rectangles. Okay, as shown there. Okay, we partition the lamina here into small rectangles, and let's consider this the rectangle here. Call it a lamina L sub k. Yeah. So there are many points in this lamina L sub k. So let's choose one point as a representative. Call it xk, yk. Okay. So you can see this rectangle has sides delta x, delta y. So they are also assumed small. So over this lamina LK, we assume the mass at the point xkyk is rho at xkyk. Okay, so we assume the lamina LK has is approximately the density of at the point xkyk times the area. The area is delta x, delta y. Okay, so this is an approximation. Okay, because in the lamina LK, we consider only one point, the representative point. So the mass of lamina LK is approximately the mass at the representative point xkyk times the area. Okay, so the mass of the total lamina is the sum of the lamina, the density of the seminas of each square here, each rectangles here. So if we have n partitions, if the lamina is partitioned into n rectangles, so we have a sum. Okay, as the summation as the approximate mass of the lamina. So to get a better and better approximation, we use smaller and smaller partitions, but that means That means increasing the number of partitions. So the mass of lamina is defined as the limit of this summation as n tends to infinity. And by definition, if this limit exists, so it is equal to the double integral of rho xy dx dy. So that is uh, the formula for calculating a mass of a lamina L that covers with a known density rho xy over region D. Okay, so if rho is a constant, call it P, then because P is a constant, we can write it outside the integral. So we have a double integral of 1 over D, and that means it is the area of D. Okay, so if the density is constant throughout the lamina, then the mass is just a constant P times the area of D, of the region D. Right? So we will discuss examples of calculation of lamina next lecture. So I will stop here, and I will show you the QR code. I hope it's working today. Where is it?